Okay, so I guess we're going to be talking about receiving antennas, and the way these forums work is it's all about you, not about me. And by the way, if anyone has anything to add, in many cases the experience of people in the audience for a particular question will be more valuable than what my own experience is. So let's get started all the way in the back with a question. Oh, that's easy. So the question is, between an 8-circle array, which is a very large antenna, there are two versions of the 8-circle array. One is the one that uses 106-degree phasing, which allows you to build the entire array in about 3/4 of an acre. And the other version of the 8-circle array requires about 3 or 4 acres. It's much bigger, but it uses a simpler phasing arrangement. Both of those are extremely high-performance antennas. They have a beam width of about 45 degrees, similar to a 5-element monoband Yagi, and side lobe levels that are in the order of minus about 20 dB down or so. So the 8-circle array is probably 5 or 6 dB better than the SAL array. The SAL array is a fabulous antenna. The shared apex loop array is a fabulous antenna for a small lot. And it's also an excellent antenna if the noise sources that you're dealing with tend to be local sources, like your neighbor's plasma TV or high efficiency motor in a furnace, for example, both bad noise sources. So small antennas are preferred for local noise sources. Very large antennas like the 8-element, the 8-circle arrays aren't very effective for local noises. Those noises need to be several thousand feet away for the big antennas to work well. So what is your noise situation? Is it local noise or do you have a quiet local? Yeah, that's great. So a big antenna would be well worth the effort. Do you have room for that? So do you have room for a 3-acre size antenna, or you do? Okay. So let me give you a little bit of a quick trade-off on those. For the 8-element arrays, there are 2 types of arrays that you can build. One is the high Z array. It doesn't require any radials. It doesn't require any top hats, but it requires a preamp at the base of each vertical. So you need 8 preamps and a way to distribute power to all of those 8 preamps. There are many failure points in that array. So it can be a little tricky to keep it running. And the directivity of the array requires that all of the 8 elements are used in the high Z array. So the performance of all 8 elements and all 8 preamps must be preserved, otherwise the antenna does not perform properly. On the other hand, the so-called broadside end fire array with passive elements, so that's a 3-acre array, is very simple. It's large, but it's a very simple array. There's no electronics in that array. Of course, there are relays to switch directions, but that's very simple electronics. There's no electronics at the base of each element. So the performance of the passive array is no better, no worse, but the reliability is far superior because of its simplicity. So, and as I mentioned to others, I love this hobby. I love designing and evaluating antennas. I hate fixing things because it means I screwed something up. So for me, because I dislike fixing things so much, I tend to favor the much more reliable antenna, so I don't have to be out there on a freezing January night trying to fix something that shouldn't have broken in the first place. Okay? Right here.
In regards to beverage antennas, they have to be absolutely laser straight, or can they curve to get around obstacles, and is the height above ground directivity?
Okay, so the question is, how critical is the installation of a beverage antenna? You know, do I need to get a transit out there and get it in an exactly straight line, or can I go around obstacles? And what happens to a beverage as I vary its height above ground? Okay, so let me answer the first question first. And how long is this Beverage?
I could go up to 500 feet.
Yeah. And 500, and it would be like a 7-foot high Beverage, something in that order?
Maybe.
Yeah, okay. But it wouldn't be a Beverage on the ground.
Don't think so.
A 500-foot Beverage on the ground wouldn't work on 160. It's too long. 200, 220 feet is about as long as you can do. And the antenna you're talking about, the roughly 500-foot Beverage, is by far the most popular receiving antenna on 160 of any of them. The great thing about Beverages is they just want to work. There's hardly anything that can go wrong with them. And the things that can go wrong with them are kind of obvious. You know, the support pole has fallen down or the wire is broken, or, something really simple. So they're a wonderful antenna, and they have really good directive properties. The beam width of a 500-foot long Beverage on 160 meters is about 65 degrees. It's pretty broad. So as long as the deviations from a perfect straight line are small compared to 65 degrees, it's not going to matter. So if you deviate 3, 4, 5 degrees to get around an obstacle, the DX will never know. So I wouldn't worry about that. Now, in terms of height above ground, for many of us, it's merely a matter of letting wildlife get under the antenna without tearing it down. So I've got lots of deer in the areas where my antennas are, so I must put my Beverages a minimum of 7 feet high so I don't wind up with the Beverages being dragged a mile down the road. And that's happened to me. I've lost some Beverages and I've never found them. So 7 feet, and of course you don't want to accidentally snag a human being either. So for most of us, 7 feet is kind of the minimum just for practical reasons. But if that's not an issue, and I've been involved in Beverage installations at military installations years ago, and we put them 4 feet high. But we had a fence all around them to make sure that nobody could get in. Because you don't want an antenna 4 feet high to be any place where any human being is going to be walking around. They'll get snagged in it. It'd be a mess. But as you lower a Beverage to the ground, their efficiency slowly gets worse. The pattern doesn't change hardly at all, which is why we put them only 4 feet high. And we were using them at higher frequencies, more like 10 megahertz. So 7 feet was too high. Beverages develop directivity because very low horizontally polarized antennas are extremely inefficient. So normally with a dipole, the primary radiation is off the sides. But when you put any horizontally polarized antenna very close to the ground, much less than 1/10 of a wavelength, the horizontal radiation is suppressed because it's so lossy. So 7-foot high antenna is about 0.01 wavelengths high on 80, so on 160. So it's almost no horizontal polarization off the side because the losses are so high. But if you raised it up to 20 feet, it would be pretty bad. It'd be much too high. And if you lower it below 7 feet, the efficiency drops a few dB, but efficiency on 160 for receiving antennas doesn't matter. So you could drop that down to 1 foot if you want, but it'd be an extreme tripping hazard. Next question.
You mentioned 20 feet's too high. I've got the deer problem. In addition, I have people on horseback. So how far can I raise it?
Find your horseback rider, measure his height above ground, and that's the minimum.
I figure 9 to 10 feet.
Yeah. You don't want to snag that would be really bad. Yeah. So it's just practical. So I mean, you do what you can do, and you don't worry about the rest, right? And if there are some areas where you don't have riders, drop that area down to 7 feet. But as long as you're well under 20 feet, it's not too bad on 160. On 80, it's a problem because 80-meter antennas start to produce significant horizontal polarization if they're higher than about 10 feet. So 160, it's okay. 80, not so much. Next question. Right in front here.
Yeah, due to severe site limitations, I would force to consider one of the 43-foot trackless verticals.
Okay.
If I put a antenna tuner at the base, and would I also need to have a maneuver with it? And if so, what would come first, coming down the
Okay. And what bands are you would you like to use this antenna on? 10 through 80, good, because it's really, really a tiny antenna on 160. The purpose of the on is just as a choke to keep feed line, to keep the power from the antenna from getting on the feed line for the most part. It's a good idea to use that. There's no reason to put it between the matching unit and the antenna. I think it makes more sense to place it between the antenna and the feed line. But putting that tuner right at the base is a good idea. If you look at the SWR performance of these 43-foot verticals, it's not that good. It's not terrible, but it's not really that good either. So if you put the tuner at the base, I think you'll be a lot happier with it.
Actually, at 40 meters, it's fairly resonant.
Yeah.
So that's at least one good.
Yeah, that's good.
Especially in this climate.
Yeah, and you know you need radials for that antenna to work well. Okay. Behind, right there.
Sir, do you see any problems with extreme changes in elevation with the Beverage? I sit on top of the ridge line over a river valley. About the only place I'd be able to put a Beverage would be probably a good 300-400 foot drop, but I'd be able to get to 500 feet in length.
So it'd be sloping probably 20 or 30 degrees downhill?
Yes, sir.
And which direction is the desired direction? Is it up over the top of the hill or down off the bottom?
Be going downhill towards your.
Oh, I think that would work great. Because here's what's going to happen. The main lobe of that Beverage antenna is going to come off the front of the antenna, and the whole thing is sloped down about 20 degrees. But that lobe is very, very broad. On a 500-foot Beverage on 160 meters, that front lobe extends up to about 70 degrees at elevation. So if you can just think, if we just took this room and sloped the whole room down 20 degrees, that main beam of that Beverage is still going to be pointing at the horizon and above. So I think it would be a fabulous antenna. Okay? Right in the back there. 9-circle array is great. The YCCC antenna is very well designed and performs very, very well. It is also an excellent high-performance receiving antenna. Many people have installed it and had excellent success. Right here?
What's happening with the 9 vertical antennas or 4 or 3? If you don't have a flat place,
Yes.
some slope, is a problem or
How much is some slope?
I don't know, but maybe 200 feet, maybe 3 meters?
Oh, that's very small slope. It's not a problem. Here's the reason. All of these arrays have a very broad pattern vertically. It's not like a Yagi where the range of angles off a Yagi are pretty small. You know, you have a peak lobe and then there's a deep null with most Yagis that are fairly high. But with these verticals mounted right down on the ground, that main lobe is very, very broad. 45, 50 or more degrees broad. So if you have small differences in the elevation of the different verticals in the array, the effect on the performance is small. It's almost insignificant for the kinds of variations you're talking about. So I think it would work fine. Other questions? In the back. Yeah. Yeah, boy, those are really good questions, and unfortunately, they don't relate very closely to my own personal experience. But the urban environment, where you have lots of local noises from very many directions, in many cases, a horizontally polarized antenna discriminates against that noise pretty well. And on the low bands, A low horizontally polarized antenna is very inefficient, but signals are very strong on receive. So I think a low horizontal antenna, it's worth trying. But how well it performs depends a lot on the details of the noise sources and what polarization they are and how close they are and all kinds of other things like that. And I've never personally used these. There was a company called Hermes that built these small loop antennas and built them into arrays. And in the professional world, they've been used widely. But personally, I've never used them. But that company was very successful, so I assume that there's some substance to it. Otherwise, people wouldn't have been buying them. But they used to mount these arrays on tripods in a line, and then they had phasing schemes to vary the phasing between the Hermes loops. But yeah. Here's why I wouldn't do that. If believe it or not, a vertical has pretty good RDF, receiving directivity factor. And why is that? Because verticals are very insensitive to signals coming in directly from above. So the radiation pattern is kind of a donut with very little response above. So a vertical makes a very nice complement to a phased array. So the vertical itself provides the insensitivity to signals coming in at very high angles, and then the phased array produces the pattern at lower angles. So I don't know of anyone who's tried to build a 160 array with loops like that. W3LPL did some experiments with that many years ago, but he hasn't done anything at any time in the recent past. So I have to assume that he dismissed them as not being as good as verticals. But he did some of that work, but it was 30 years ago. All the way in the corner. I can't hear you. Unfortunately, I don't recognize any of those names, so tell me more. Yeah. So these are antennas intended for what? Portable use? Okay. In my earlier presentation today, actually 2 times, we talked about the advantage of horizontal polarization. The efficiency is wonderful if you can get the antenna high enough, and high enough generally means 1/10 of a wavelength or higher. And one of the communities, the Summits on the Air community, SOTA community, almost all of those folks have gone to end-fed half-wave horizontally polarized antennas, which they try to put up 10 or 20 feet in the air, and have found that to be a absolutely superior solution to anything else they've tried. And the reason for that is because of the inherent advantages of horizontal polarization, as long as you can get them up in the air. And using the end-fed arrangement just simplifies the whole thing. You don't have to deal with coax and all of that kind of thing. It's a little bit of compromise to the end-fed, but not very much, because most of the radiation from a half-wavelength wire is from the middle, not from the ends. So that's my own opinion. And I haven't had an opportunity to experiment with these other arrays, but I'll tell you, did you see the presentation I gave on how to do quantitative performance measurement of antenna performance? You did. So there's an opportunity for you. Now there's a technique where you can measure repeatably the relative performance of antennas. It's a brand new development, just started. We only started the experiments less than a month ago, but it is very, very promising for highly repeatable quantitative measurement of the relative performance of 2 antennas in the same site. And it's very resistant to the gee, I just invested all this time and money in the new antenna, it has to be better, which biases the testing. Testing using the whisper light methods eliminates all those biases towards the new antenna, which isn't, it's a human tendency. We'll spend a lot of money doing a new thing, and you're going to be biased towards a good result for the new thing. You can't. It's hard to get that natural tendency out of any test process, whether you're testing a $100 million defense project or a $58 antenna. That human bias is there, and these quantitative methods strip that out. So I'd encourage you to try it. Yes.
Yeah, comment, Frank, on the summits on the air folks that have the infed antenna and horizontal antennas. They're also, even though they're only at 20 feet, it also helps if they have 10 or 12,000 feet on the mountain peak.
Oh, of course. Yeah, of course. And that's,
Which is pretty good.
yeah, that's right. So do you do these SOTA de-expeditions?
Yes.
You do? Yeah, that's great, yeah. Well, and the reason it works so well, so if you're on a mountain peak, there's a little bit of earth under the antenna, but you go out 20 feet and the earth is down 20 or 30 feet where it doesn't affect the lossiness of the horizontal polarized antenna. As you know, if you're involved in that community, they very much favor horizontally polarized antennas. Simple, and they work good. Yep, and very inexpensive. Yep. Yes.
Is there any wire material to avoid using for beverage antenna?
I didn't hear the word. Is there anything, what to avoid?
Is there any particular wire you should avoid using for beverage?
Okay, that's a good question. So the question is there any particular wire to avoid using for a beverage? First of all, the beverage is a lossy antenna, so adding a little bit more loss from the wire you use is not a big deal. And you get plenty of signal on 160 meters, so you don't care if there's a little bit of extra loss because you used, let's say, galvanized steel wire instead of gold-plated whatever. So the answer is it doesn't really matter. The consideration is mostly mechanical. You don't want unintended wire breakages. You probably don't want to use galvanized steel because eventually it'll rust and break. So I think it's mostly practical mechanical considerations rather than anything to do with electrical performance. If one wire provides 1 or 2 dB better performance, you'll never be able to tell because on 160 meters, noise dominates everything. Okay, next question. Yes.
Frank, this is not a receiving end kind of question, but you talked about inverted L's over at 60. How many radials do you think this is?
Okay, how many radials do you need? And that applies to any antenna, right? Not just an inverted L. How many radials do you need? And I'll bring the receiving antenna question in here so people don't wonder what I'm doing here. On receiving antennas, radials only provide stable feed point impedance. That's all they're for. So it's a fundamentally different situation on receiving antennas versus transmitting. On receiving antennas, it's feed point impedance stability. And when you've got enough stability, which is usually plus or minus 10%, that's good enough. More radials don't help. But on transmitting antennas, the situation is fundamentally different. What you want is you've spent a lot of money building your station and buying an amplifier, and you don't want to heat the worms unnecessarily. So you want enough radials to do that. There have been a lot of articles written over the years on how much wire you should use, and if you want to economize on the wire, what length should it be? And a generally accepted rule of thumb is you should shoot for a minimum of 16 radials. And if you can only put in 16 radials, then something in the order of about 0.15 wavelengths is good enough. So when you have a small number of radials, having them really long doesn't help very much. So you should shoot for 16, but if there's nothing preventing you, it's even better to go to 30. And once you've gotten beyond 30, the return on investment is pretty small. Now with this new antenna performance method that we now have for the first time ever, we can answer these kind of questions in a very quantitative way. When you change the number of radials, you can tell whether you got any benefit or not. But you never could do that until the last month. Yes? Yes, that is correct. And in fact, the very first thing that I did with the manufacturer of the soda light transmitter was to recommend to him a way so that he could always transmit simultaneously with a pair of soda light transmitters. Sequential measurements are very inaccurate. The ionosphere changes rapidly, and it adds. What we wanted was measurements that had accuracy in the order of 1 dB, plus or minus 1 dB. That was the objective. And when we tried to do that without simultaneous transmissions, we just weren't there. We were just getting rough estimates of performance. But as soon as we went to simultaneous transmissions and two antennas that are co-located, a reference antenna and an antenna being tested, for example, a Yagi at 30 feet and then a dipole maybe 50 feet beside it at the same height, and then you compare those two. We have not yet begun to try to test antennas that are miles apart. We are going to try that. We're going to try to find some analytic methods that'll work, but I think it's going to be really difficult because what's happening when antennas are very far apart is the signals are traveling through different parts of the ionosphere. So, but when the antennas are co-located, where you have a reference antenna and an antenna under test, that works very, very well. But there's a lot more to be learned, and I'd encourage anybody that wants to get involved in this. A pair of whisper transmitters is not very expensive, and then you can start getting involved in some of these tests that have just started. This is the last question in the back.
I could probably look up the answer, but what's the best radial wire to use for radios?
What's the best radio wire to use for radios? The consideration is almost entirely mechanical. So you don't want to be bothered by broken wires. And broken wires can happen through primarily two ways. One is by human beings or animals tripping over it, and the other is through corrosion from contact with soil. That might, especially if the soil is a little bit acidic. So so it turns out copper is pretty resistant in most cases, but there are some soils that are extremely corrosive to copper, and if you have that kind of soil, you probably know about it. If you have very corrosive soil, there's no problem at all using insulated wire. It works just as well, and that'll protect the wire from the soil for corrosive soil. If you don't have corrosive soil, you can just place copper wire directly on top of the soil. I discourage people from using galvanized steel because it fails too quickly. Okay, so that's the end. Now, you folks can talk to me here in the hotel any of the nights during the convention, but we have to move on to the end of the program. Thank you very much.